Hi, so here's the buffers extension question, a worked example. And I think the question was, with the following equipment, let's write it out, with the following equipment, we need to make a buffer. So make a buffer of pH 4.2. And the equipment is 1 molar ethanoic acid. Let's call it HX. All right, let's call it HX to save us some time. And we've got some 1 molar sodium hydroxide. Just to make it a little bit more complicated than sodium ethanoate. We've also got a pH probe and the normal lab equipment. Let's write down pH probe anyway, because that's important. And we can say you're not allowed to look up Ka because your temperature is going to be different to 25. Okay, so working through the answer. Normally in exam questions you're given Ka, and when you've got a buffer question like this, but we're not given Ka. And so then first of all, first thinking step, I suppose, is that they have to realise that, and then they're going to ask themselves, well, how can we get Ka? And hopefully the students I gave this to didn't come up with this on their own. They needed a bit of help. Never mind. They could just make up a random buffer and measure its pH and work out Ka in reverse. So that's what we're going to do. We're going to make a random buffer. So we don't know what the pH is going to be, but we do need to remember that moles of sodium hydroxide needs to be less than moles of ethanoic acid. All right, so they're both 1 molar concentration. So let's have 100 cm cubed of ethanoic acid, and let's say 50 cm cubed of sodium hydroxide. We chuck them together to make our buffer, and I don't know what the pH of that would be, but let's say for argument's sake that you dunked your pH probe in there and you found the pH was 5. Okay, so you find that the pH equals 5. Now we remember that the Ka expression, and that's going to let us find Ka in the end. So, but first, if we've got the pH of 5, then we're going to want the hydrogen ion concentration. Right, so the hydrogen ion concentration is going to be 10 to the minus 5. There we have it. And then we can write out. So then we can write out the expression of Ka. So it's the hydrogen ion concentration times our X minus over our HX. Now, normally this would be concentration in a normal equilibrium equation, but because it's buffers and we've got the volumes cancel out, we can call them moles. Concentrations being moles over volume cancelling, so this is all fine. Right, so we know the moles of X minus ethanoate, the moles of ethanoate is, the moles of the hydroxide that we added. So that is moles of hydroxide that we added is 50 over our volume times our concentration. Concentration was 1, right? So our moles of ethanoate is 0.05, like so, and our moles of HX is whatever let's call that moles of HX at equilibrium, or in the buffer. Yeah, let's call it B for buffer. Moles of HX in the buffer are moles of HX right, that we started with, and let's call that HXS, minus what reacted away, which was our 0.05, the amount of hydroxide that we added. So we put that in. Okay, so moles of ethanoic acid that was started with is 100 over 1,000. We put 100 cm cubed in there, so that's 100 over 1,000 dm cubed times our 1 molar concentration minus what was reacted away. No, it's just 0.05, and that is 0.05 as well. So we got 0.05 of HX. So then your 0.05s are going to cancel conveniently, and we can say, all right, and we can say that Ka is 10 to the minus 5. All right, times 0.05 divided by 0.05, so 10 to the minus 5. So now we have Ka. That's good, but we're not finished. So we have to now make this buffer with a pH of 4.2. How are we going to do that? So what we have to do is we have to decide how much ethanoic acid and how much sodium hydroxide to dunk in together. That's two variables, so why don't we just turn it into one variable by saying that, well, we're just going to chuck in 100 cm cubed of ethanoic acid, and then we only need to work out how much sodium hydroxide, right? So we're going to just write that down. We are going to start with 100 cm cubed of ethanoic acid. We'll call that HX. All right, and the question is how much. Question now is how much. What's the volume of sodium hydroxide we need to add? All right, to make it a pH of 4.2. Of course, what one group were tempted to do before I stopped them was to add it bit by bit until they got the right pH, and they didn't have to calculate anything. They just measured how much they added bit by bit. But as the question was to work it out first and then add it all in one go, I made them do it the long way. But I did give them credit for a little bit of ingenuity there. So let's do it the proper way, the difficult way. If we want the pH to, so we've got to work out how much sodium hydroxide that we're going to add. And what we know is the pH must be 4.2. So if the pH equals 4.2, right, then hydrogen ion concentration is going to be 10 to the minus 4.2. Like so. We can leave it at 10 to the minus 4.2 for now, rather than putting it in a decimal. And what we're going to do now is substitute that into our expression for Ka in the buffer equilibrium. So we've got Ka equals 10 to the minus 4.2, our hydrogen ion concentration, times the moles of our X minus, our ethanoate, divided by the moles of our ethanoic acid, let's call it HX, but at equilibrium, yeah, or in the buffer. We called it B, didn't we? So that's what we know. But we've already worked out that Ka is 10 to the minus 5, so we can put that in there. Right, I'm going to need to start a new page now. So going to go on to that. So the thing is, the HX that we had in that expression, let me write it out again because you sort of need to see it. So Ka was 10 to the minus 5, and that equaled our 10 to the minus 4.2, which is a hydrogen ion concentration, times the moles of our X minus, our ethanoate, all over our moles of our the moles of our ethanoic acid in the buffer. So there we had it. So this moles of ethanoic acid in the buffer is the moles in the equilibrium, of course, not the moles that we added at the start by adding 100 cm cubed. All right, but what we do know is, all right, so we can go where what we do know is that the moles of ethanoic acid in the buffer equals the moles of ethanoic acid at the start, when we dumped in 100 cm cubed, minus what reacted away, minus the moles of our hydroxide ion. That's what we reacted away, and this is the unknown. Okay, so we can just work that through. So the moles of ethanoic acid at the start was 100 cm cubed again, wasn't it? So that's 100 over 1,000, and our concentration was 1. And this is what we don't know. So we'll leave it like that for now. And now we're just going to substitute those in to this first equation. All right, so then we've got 10 to the minus 5 still equals 10 to the minus 4.2 still times moles of our hydroxide divided by this, of course, is 0.1. All right, so we're just going to say 0.1. 0.1 take our moles of hydroxide, and now we're just solving for moles of hydroxide. So we might as well do it. I might as well carry on and do it. So we're going to just multiply out. All right, so let me do that over here. So you got 10 to the minus 5 brackets 0.1 take moles of hydroxide equals 10 to the minus 4.2 times moles of hydroxide. Right, okay, so let's multiply that out. So you've got 10, let's go back here to give us some more space. So 10 to the minus 5 times 0.1 turns into 10 to the minus 6. So we've got 10 to the minus 6 equals, or take, let's say, let's do it line by line, 10 to the minus 5 times moles of our hydroxide equals 10 to the minus 4.2 times the mole of our hydroxide. Right, and then just 10 to the minus 6 then becomes equal to 10 to the minus. I've had a little glitch, so we're going to start from where we left off. So I think where we left off was we had 10 to the minus 6 equals 10 to the minus 4.2 times the moles of hydroxide plus 10 to the minus 5 times the moles of hydroxide. Right, I think that's where we got to. All right, so we're just going to simplify that, taking moles of hydroxide out. So that's moles of hydroxide times 10 to the minus 4.2 plus 10 to the minus 5 equals 7.310 times 10 to the minus 5 dot moles of hydroxide. So our moles of hydroxide is 10 to the minus 6 over 7.310 times 10 to the minus 5 is 0.0137. That many moles. Therefore our volume of sodium hydroxide equals our moles, 0.0137, divided by our concentration in decimeters cubed, which equals 13.7 cm cubed, and that is the answer. And out of my 20 current A-level students, 2 of them got there, 2 of them got this answer, but they did need a couple of hints. So they first needed a hint about experimentally determining Ka, and then with the equation that ended up only having moles hydroxide as the unknown. They needed a little bit of help with that. But apart from that, they got through it, and they made a buffer that was proven to be the right pH. I hope that's helped.